first of all, I would like to thank Arjun and basically the STEM Stamp to give me this opportunity to present some of my research here with Professor Aditya Karnataki. And I would also like to thank my professor himself because he was the one who motivated me for this thing. Otherwise, I would have just dumped this thing. And special mention to Professor Sneha Chaudhary. She was the one who introduced me to this problem. She is the one who works in this visibility problems. You would also see her in some of the results which I will present today. So without any ado, let's start. So these were the prereqs which are for this talk, and we will straight move on to the. So, how many of you know about Farey sequences? Okay, I can see some hands from this side. Okay, I can see some hands. Cool. So, any one of you would like to just give a quick thing about what is Farey sequence? What it is? Any one of you can. Maybe I can. That's fine. So, okay. So we start with the following definition. Q So basically, the FQ is the set of all rational numbers which are in between 0 to 1. This is the best description you can have, where the denominator is bounded by a positive given positive integer. Fine. So let's have some examples. For example, f of 1 is defined as 0, 1. So these are the starting ones, and then I'm jumping because you can get the things by yourself also. I just want to emphasize how the set looks like. So you must be wondering why I'm writing these things as 0 over 1 and 1 over 1. This has some emphasis which you would get through in the later part of my talk. But yeah, so everyone is clear with the definition of Farey sets, like how F1, F2 and F5 is defined, right? So okay, by this thing, can anybody make a small observation about cardinality of the Farey sets? Yeah, sure. So, right. Can you, so suppose n is a given positive
n minus 1 का cardinality plus 5.
Right. Exactly. So, n is n minus 1 plus 3 of n. So, I think everybody knows this nice function. This is Euler Quotient function. This is also multiplicative. Right? Okay. Right. Right. So this implies that we can write the cardinality. So I would like to define the cardinality of f. You can write fn, but in my notation I'm writing it as nq. This thing as very well told about. This is 1 plus summation q from 1 to capital Q phi of. Right. So now we call this thing, this funny thing, to be a summatory function. Summatory function of, so function of allocation function, n, or let's say in better way phi of k, where k runs from small to q. Right? We call it, this is some notation, because then essentially we will just denote this thing by something known as phi of q, big phi. Fine. So it's a very well celebrated result that n of q is 1 plus so like this thing is 3 over q square I square plus O of q log big O. So this is one thing which we aim to prove in today's talk, and this has something to do with co-prime numbers, which you can even see by the definition of the Farey sets. So our aim would be to first, so if somebody can see just from these expressions, like they have read some bit about this topic, they can just bluntly say that it is somewhat related to probability of two numbers being co-prime, right? But yeah, like how this big thing relates to that thing, we will see in a few moments. But I want to stress about this thing a bit more, because so interestingly, one nice property about this phi q is, or this particular summatory function is that, so suppose I am writing this thing, this can be also written in this following manner. Summation b divided by m. So I think one can observe why so. Right? Can anybody give me just a quick sketch of why this is true? So, okay, essentially if you write m, so d divides m, so just check this way, not this way. D divides m, so there exists an integer n such that m is equals to nd. Then what you do is you use the property of the fact that phi k is multiplicative, and use the fact that mu d is defined in this the following way which I told earlier. If you write everything here, you will just realize that it is explicitly writing phi of k because of the multiplicative property phi k. That's good. So this thing can also be written in the following fashion. This particular sum, which I am going to write.
This can also come from the division and convolution, right?
Yes. Right, which is known as Mobius inversion. Right. So one can think it in that way, but yeah, I mean, I wanted to make it as elementary as possible. So right. So this can be also thought of in this following manner, which is just switching sums in a particular way. Right. So this thing, so I'm erasing this part. Is it fine? This thing can be also just written as in this following. So I'm just running this sum now. So this comes out to be this particular thing, and this particular form has its own beauty. Everybody can see what I have written, right? So it's mu sum d runs from 1 to n, mu d times floor of n over d times 1 plus floor of n over d. This is one of our important results to study about some asymptotic form of the summatory function. Yeah. So yeah, this is basically about the, like, from just the definition we got these kind of things itself. Now, very quickly I would like to also define something which is known as neighbors of Farey fractions. So can I just say this? Is it fine? So I don't want to spend much time on this, but like I will just give some definition of what we call as neighbors of Farey fractions, so or consecutive fractions. So suppose I define gamma I as ai over qi and gamma I plus 1 as ai plus 1 over qi plus 1. Then they are said to be consecutive fractions in FQ. In FQ, if and only if. So you can just read it as a definition. If and only if they satisfy the following relations. First is that ai plus 1 qi minus ai times qi plus qi plus 1 is 1. Can anybody just, oh sorry, so I write it in format. Can anybody think of this expression in some another way? Does it sound familiar with something? Exactly. Determinant of this particular thing, which is ai, and then you have qi of ai plus 1, ai and qi plus 1. So we say that this funny thing is in SL2 of Z, whatever that means. This just means special linear group with coefficients in integers. So this just comprises of 2 by 2 integer matrices whose determinant. Right. But why such a form is there? That is due to the fact we treat these ai qi's and ai plus 1 qi plus 1 as vectors, and then you show that basically, or to have a neighbor kind of property, they should satisfy some transformation, and that transformation has to be invertible from Z to C. So yeah, that is one such motivation to define it in that way. And second is that so qi plus qi plus 1 is greater than q. This is how we define. So yeah, if they satisfy this thing, then we call them as Farey neighbors. And we also, so we call Farey neighbors to be adjacent if you add one more thing, which is so we call gamma I and gamma I plus 1 as are adjacent to Farey fraction gamma I, gamma I minus 1, are adjacent to gamma I if it can be, so the gamma I can be expressed as follows. ai minus 1 plus ai plus 1 over qi minus 1 plus ai. So a nice exercise would be to spot some Farey neighbors and some triplets of Farey fractions which are which satisfy this adjacent property in FQ. For, let's say, take Q to be prime, then what you can do? Take Q to be a power of prime, then what you can do? And then so on. Because interestingly, for some particular values of Q, these adjacent triplets are somewhat very nice, which you will observe. They have some nice properties about their denominators. since that is not the aim of the talk, this is itself an area of discussion. I don't want to go further on this, but I wanted to just introduce what are Farey neighbors and what are when we call Farey neighbors to be.
Piyush, all your Farey things were in neighbor order, right?
Right, exactly. That was one of the observation you should have made. That all of these things, like these elements, are in the prescribed order of A is less than Q less than the capital. So, yeah, I mean, when we write Farey sets, we usually want to write them in the following manner, because this thing is called as median. So, for example, if I pick, let's say, if I pick these two guys, 1 over 2 and 2 over 3, I want to check if they are adjacent. That means if 1 plus 2 and over 2 plus 3 is basically in between them, and interestingly it is, which is 3 over 5. So these guys are adjacent, and so interestingly 1 over 2 and 2 over 3 are also Farey neighbors. So these things go if and only if. That is a nice exercise to prove, so you can also try it. Right. So now we move on to something which relates this Farey Farey fractions to visibility problem. And so I would first like to introduce you with the notion of visibility. So till now everything is fine, right? So I will not write much definitions. I will want to introduce this concept through more visualization. So suppose we have the Z2 plane, and suppose this is the origin. So this whole concept of visibility was itself is very old. This was studied way back by Sylvester in 1880s, where he first took some families of straight lines which pass through origin, and then, so suppose I take some families of line. So by families of line I mean which pass through origin, they have some unique representation, which is y equals to mx. We take m to be in positive rationals. That means we are just restricting ourselves to this particular particle, first part. So 0, 0, and suppose I am taking some families of line. So he said a point A, B is said to be visible. If so, A, B lies on one of the lines from the family. So lies on one of the lines in the family y is equals to mx, and suppose you have this point A, B here, and you have a straight line which joins A, B. So of course, given any integer point, you can have such a straight line, right? So for every A, B, there is a unique straight line which passes through 0, 0 and A, B. So what we say, we say that A, B is said to be visible if it lies in one of the lines, which will, and there is no another lattice point on the line segment joining 0, 0 to A. Basically, suppose you are sitting at origin and you are seeing points in Z2 plane, then if the first point that you see is A, B and no another lattice point, then you say that it is visible. So it is literally, in the literal sense, it is called visible. So right, is visible if it lies on one of the lines in the family this, and there is no another lattice point C, D, which lies between So this is what Sylvester came with in 1883. So I just this is by Sylvester in 1883. So one thing which is interesting about this visibility, this notion is that a point A comma B is visible if and only if they are open. And you can make this observation very easily. Suppose, so which direction you think is the trivial one or the easier? Right, so GCD A comma B implies the point is visible. It is much more easier because suppose they are co-prime, then by these roots there exists x and y such that ax plus by is 1. Now what you do, so basically you take cx comma cy where c is any non-zero integer, then you would basically get all possible points that lie on this line, and you can form an equation of a line which comprises this point. Now a point is visible implies GCD is 1 is similarly simple because so that point has to lie in this line, and suppose if there is another point c comma d for the sake of contradiction which lies on this line, then you show that basically that cannot be possible because or basically if GCD of A comma B is not 1, then it will not be possible. C comma D has to be in between, because so for that thing you would require just the simple fact that C and D are just less than A and B, so you can represent them uniquely with their GCDs, right? So yeah, so this is a simple observation which you can make here. This notion have been generalized by many authors very differently. By generalization I mean that so this Sylvester took families of straight lines, but then people started generalizing this with families of power functions, then polynomials and whatnot. So I would just like to write some results which people came up with, and then we would, so the aim of the talk is to introduce some results regarding the visibility problem, and then proving the fact that the cardinality of the Farey set is 3q square over pi square plus O of q log, which essentially would amount to first proving that probability of two co-prime, like probability that two numbers are co-prime is 6 over pi square. Okay. So can I erase this? So I would just like to write some bunch of results which people came up with this visibility notion, as in, so the idea is same. You want to have a curve and it should pass through curve in Z2, it should pass through 0, 0 and A, B, and there should not be any lattice point between the segment or between the part of the curve which joins 0, 0 to A, and then you see that that point is visible. That is the same setting which have been done. Just from straight lines they have taken power functions, they have taken polynomials, and in our work we have generalized it to families of circles, which I would like to come in just a few minutes. So any doubt with the definition? So right, so Sylvester defined this definition in 1883 and proved that density of all the visible lattice points, let me call them, so suppose the set of all visible lattice points A, B up to n is denoted by V of A, B, then he proved that density of V of A over V is 6 over pi square, which is 1 over zeta. Those of you guys who are not familiar with zeta 2, forget it. It's not anything important to know about. But the interesting thing about density, so this density is the natural density which we are taking here. I would just like to define it. So for a subset S of N2, we say density of S as this. If this limit exists, then we define it as density of S. This is called as natural density of set S. So what Sylvester proved in 1883, is that density of A of A comma B. So the limit essentially is 6/6. And then people further generalized it. So this was 1883 when Sylvester came up with this thing. Then Christopher in 1921 proved that, so if you extend this notion of straight line to, instead of Z2, if you extend this notion to Zk, then density of all those such visible lattice points, I call it Vk of A comma B, is 1 over zeta of k, where k is greater than or equal to 2. And so just to define it for you, for the audience, zeta of S is defined as inverse to S 1, where real part of S is you can take 0 itself. So this is Riemann zeta function, and we have, of course, it's the most celebrated function in analytic number theory. Some of the results also go into proof, assuming some results about Riemann hypothesis, and maybe some of the results in Farey sequence. One of the results is equivalent to assuming or equivalent to proving Riemann hypothesis. So in that way, some of you who is interested in Riemann hypothesis can also look about Farey sequences. So yeah.
Real part of f greater than 0 is not required, it just does not exist as a
Anyways, we have an extension for zeta S, but as a definition, I want to define it in that way. So this is Christopher, and then this notion. So this was in. So what Christopher did, to say in the simple terms, is instead of taking the plane to be Z2, he took Zk. So imagine it as k dimension thing, where so all the there is a k tuple thing. It's a vector, and the straight line is comprises of points which are k tuples. And basically, Christopher proved that for all of those points, if you define visibility in similar notion, then it comes out to be 1 over zeta k. So just to make this quick, this was Christopher. Then a remarkable step was taken after it. So people didn't did much after it, but then in 20, so okay, Coins, Harris, and Cubic, and Mibrica generalized this by taking or maybe introduce a new notion of visibility by, instead of taking straight lines, they took power function. So they defined it for the family fx is equals to ax raised to b, and they called the points to be b visible if the points lie on the curve, and they satisfy the visibility notion in the similar fashion. So they proved that if you assume the same set of all visible points up to n, then their density, he proved that it comes out to be 1 over zeta b plus 1. So if you take b to be 1, then this recovers the Sylvester's result. which is because when you plug 1 it is 1 over zeta 2, which is 6 over pi square. So they proved it for this particular power function ax raised to b. And
One sec. If x equals to ax, like, what is this fx actually?
right. So it's in this way, mx raised to b, where b is fixed, we call it to be b visible, and m is the parameter which defines the family. Right? Okay. So then further this notion took a more turn, where Harris and Omar came up with more generalization. So they suggested that what if for power functions you take, so instead of just taking this plane, what if you take the negative side of the plane also? So they observed that it does not change the result much. Instead of 1 over zeta plus 1, it comes out to be 1 over zeta, the density. But they have taken the same power function mx raised to. Okay, so these were the results regarding the power function. But now recently, this notion have been generalized to polynomial, any arbitrary polynomial. Maybe so. Can I? Maybe I can explain this thing. Is it fine if I remove this one? Yeah. So recently, the group of people generalized this notion to any family of polynomials. So as in the set there, or the family is basically in this following fashion. Where ai's are integers, q is a positive rational, and okay, so GCD of all of the coefficients is 1. So we are taking this part. Though it really doesn't matter if some, like if there's a prime which divides every coefficient, because you can just pull it out and then it would be outside. It does not change the density much. That's why we have taken this family. And these guys prove, so the notion for visibility is again same, that if a point, let's say r comma s, lies on this polynomial, then let's say you join the polynomial from 0 comma 0 to r comma s, then there should not be any lattice point on the curve 0 comma 0 to r comma s. Then you say that r comma s is polynomial visible, this polynomial visible. Interestingly, open problem in their result, which is still unsolved, is following. So in all of the results, you can see some if and only if criterion, as in a counting criterion which can give you a nice asymptotic density result. Or though density is in terms of limit, but the cardinality of basically the set of visible lattice points in some asymptotic result. Because you can see there is a equivalent thing here. An open problem in this area is that there is no such criterion, as in people have not found any if and only if criterion to say when a point can be said to be visible. As in they have proved this way that if GCD, the natural way, that if GCD of PA comma B is 1, then the points are said to be polynomial visible. But the other way around is not true, and we don't know if there is such is there any such GCD condition which can help us to count all visible points. So whatever results, first of all I would like to mention the result. Yeah.
Can I ask a question? So have people studied like the situation where, let's say, the degree is sort of varying instead of degree being fixed? Like for instance, like f of x equals mx bar b. what if I said m equals 1 and b ranges over all positive rational numbers?
Right. So this also have been recently done. I'm not sure about the author, but yeah, there have been some results very recently about fixing m and fixing m and varying the degree, which for the
It has
polynomial.
to have b rational numbers because otherwise it
Right.
won't be, it'll be sparse otherwise.
Right. And people have also studied some correlation between the points. And a very recent paper have been there in Indian Institute of Sciences regarding that. Right. So people do have studied that, but in their result, they have taken a polynomial with integer coefficient. So this is a open problem in this section, which even I was working with the first author of this result. So we haven't got anything yet, but of course people are motivated, are always invited to do some work in this. So the result they have proven is following: that density of, so call all the visible lattice points, polynomial visible lattice points, as L of A comma P, then they have proven that it is 1. But in terms of counting the cardinality, they don't have any asymptotic count of the cardinality. So this result is a more of not a, so all of these results you can see are bit inspired from analysis, or some analysis have been done, but here a different approach have been taken where they prove visibility, or like the result using sieve theory and your famous inclusion exclusion technique, but in a more interesting manner. So you can check their paper regarding the proof of this result. So these are the results till now, which are about density of visible lattice point for polynomials. Recently we have generalized, so I may erase this. So recently we have studied the density problem for circular arcs. So we have changed the curve, instead of, so we have moved from the discussion of polynomials to circular arcs, and to just quickly define what we are doing. So we are taking families of circles, and so we have considered two specific families, which is one which looks like this and one which looks like this. So that means it is either, sorry for the bad writing. So this is one which is touching circles of family, and this is one which is intersecting families of circles. These two are the only interesting one, because you might ask me why not concentric ones. You can check by the notion itself, it's not a nice way to define visibility. So that's why we have taken only these two cases, or we can say these two cases only matter. So basically the notion is again same. So you have a point, so circles should pass through 0, 0. And suppose, so the families that we are taking here explicitly I should write. So in first case the family that we are working with is this, and in the second one, this first, this is second, and in the second we are taking C lambda, which is this one. So these are the two families that we are treating. So one can check that these two are specific, as in, so this family is about all of those circles which touch at 0, 0, and these are all those families which intersect at 0, 0 and point -1, -1. But since we are proving a density result which is not dependent on the nature of the curve. Of course, it's dependent on the nature of the curve, but not how you are, like what the points you are taking. Because you can, of course, do translation and rotation to like whatever intersecting circle you will take. You can just make them to this kind of equation, anyways. So we are considering these two for our simplicity of doing the work. So these two families we are defining, and how are we defining the visibility notion is as follows. Suppose point A comma B lies on the family. So similarly we will define it for the intersecting case. I'll just save my time and define it here. Suppose a point A comma B is on the circle. We say that a point A comma B is visible again if there is no lattice point on the arc joining 0 comma 0 to A comma B, given that the points are in this first one. So as in this will enforce some particular things.
Can we again reshape the definition of
Right.
persons?
Right. So I'm just going to do that. Just I'm first of all defining the motivation and then I'll write a formal definition. So 0 comma 0 to A comma B. So we say there is no we say A comma B is CT visible if there is no another lattice point C comma D which lies on the circular arc joining 0 comma 0 to A comma B.
So let's see, think of light rays traveling as such.
Exactly. That is how this problem is modeled. So in this setting, you can think of visible lattice points as some rays, as he mentioned. But a more interesting way to think about this problem is not when a point is visible, but when a point is invisible, as in when it will not be called visible. So suppose there is a point C comma D which lies in between them. Then if you join the line segment 0 comma 0 to C comma D and 0 comma 0 to A comma B, then the slope of the line joining 0 comma 0 to C comma D and the line joining 0 comma 0 to A comma B would be larger, as in D over C would be greater than B. Can you make this simpler? And just using this very simple observation, you can define the visibility notion, because now I go into the formal definition. So we will just say that a point is visible if there is no such C comma D which satisfies this thing. So I'm just writing formal definition.
I see now why Farey sequences come like this.
Right. So definition. This is so the definition of CT visibility is as follows. So a point A comma B CT visible from the origin if A comma B lies on the CT. So you can get I'm skipping some like steps on the definition. By lying, it means that so A comma B will lie on this circle, so it will satisfy this equation. So equivalently A minus, so you can get a equivalent form for T, that T comes out to be A square plus B square over 2A, which is a positive rational. So with that equivalent thing, you can say what will be the equation. So if it lies on the family of one of the circles from the family, and there does not exist any integer pairs C comma D in such that 0 is 0 D less than A, and C over, so D over C is greater than B. So in Z2, and of course it's lies on C2. So if you are not able to find any such C comma D, then you say that the point A comma B is visible. Or equivalently, the slope of the line joining A comma B from 0 comma 0 to A comma B is the largest. And that gives you very wonderful result. So similarly, you define it for C lambda also, and that gives you some very wonderful results. Since I am like less on time, so I just quickly say what the result is. So suppose the set of all CT visible points is denoted by T. Then we have, so rather I should write it as zero. This is the main result of which we have came up with. So suppose Vt is the set of all CT visible lattice points, then density of Vt is also 1. So you can see there is no analysis here. And secondly, density of V lambda. So we call set of all C lambda visible. So we similarly call it C lambda visible points, and so set of all. So basically, density of V lambda is also 1. So that in and all generalizes to say that for any family of circles, visibility problem. So the density of the visible points is 1. So some more talks on this. First thing is that notice that if a point is CT visible, then it is coprime. Why? Because so there is some equivalent notion of counting CT visible lattice points. So Arjun, can I extend it? It's fine if I take 20 more. So I just write some equivalent notions in how you can, so how we approach this problem, or how we define the Farey, where is the Farey thing. So one observation you can make from here, or a lemma which I would write would help to observe, is that if a point is coprime, like the 2 points are coprime, then they would be CT visible. Similarly, there is a GCD function which also says if that GCD thing satisfies, then they are V lambda visible. If that thing is true, then definitely they are said to be CT visible, right? So if I want to construct, like Farey sets, the fractions, then if I impose the condition that when I say fraction, I implicitly want to say that they are coprime, A over B is coprime. But then when I say that they all are CT visible, they are all CT visible lattice points. So essentially, if I want to define a Farey set here, that would be isomorphic to the original definition, right? So I cannot go with that kind of thought. So instead, we define this set, which is in this way. So S for a given integer n, Sn you define it as all A comma B into such that there exists. So we say when a point is not visible, when a point is not visible, and we define this set Sn, and then we count some points. So our proof also goes on basically estimating Sn for CT visibility. So yeah, I just write the description, A being N2, this thing, C as A, such that this cube fraction that means that it's some square. So suppose I define this set Sn, then we claim that basically proving S cardinality of Sn over n square going to 0 will prove that density of Vt is 1, because so as I said, instead of studying when a point is visible, we have studied when a point is not visible, when it is not called CT visible. So there is an equivalent notion which says that this fraction, if this hypothesis satisfies that there exists such a D between 1 to A, such that this particular guy is is a perfect square, then the points A comma B are said to be not, or are said to be CT invisible. Right? And then we proved that if Sn over n square, the cardinality of Sn over n square goes to 0, then basically that essentially will solve this problem that density of AT is 1. And we use, to prove this, we use a lot of techniques of sieve theory. Basically, the whole proof is motivated by something known as sieve theory, where we estimate the Sn. And so by sieve theory, I mean that I want to emphasize on this thing that we know cardinality of Sn, we know our asymptotic bound for cardinality of Sn. So we know Sn is small o of n square in a nicer way. So the whole thing, which you can see even here, transitions to something known as Brahmagupta's Pell's equation, and we check some conditions over the coefficient of the Pell's equation. We check when a Pell's equation can have solution over Fp where P is prime, and then we run some particular kind of sieves, and then we prove that cardinality of Sn by n square is 0. Due to shortage of time, of course, I cannot discuss proof of this, but yeah. And for this density of V lambda, for this thing we also have an equivalent notion. But interestingly, for proving that density of V lambda is 1, we use something known as Bomberi-Pila argument, which basically bounds number of integer lattice points over irreducible curves in Z2, whatever that has to mean. But yeah, that are the techniques we use to prove this result. But interestingly, we said that, so where is the Farey thing again? So the Farey thing is in this thing itself. Instead of taking fractions, because as I said, if I take fraction, then that would be just in bijection with the, or in one-to-one correspondence with the Farey, the original Farey set. So instead, we take the tuples itself, and then we just do this thing that we, instead of saying there exists, we say there does not exist any such D and D such that this argument is satisfied, and we basically, find the like Sn explicitly. So as in S of 1. So the notations are different. Let's call it S star for the moment. Then so basically S star of 1 is nicely this set. I want to emphasize on this set explicitly because if you solve it by this condition, you will realize that S star of 1 to 7 do not skip any points, as in they comprise of all such A comma B's such that A and B are between 1 to n, where n is, let's say, 1 to 7. But when we go to 8, it is basically all those A comma B's between 1 to n. Let me call that as, let's say, S of A comma B, but it excludes one point, which is 4 comma 8. So it's a, maybe you can take it as an exercise. Why? So, and this way we have defined something known as so we call it as circular Farey set. We define it as circular Farey set, CT circular Farey set, where we, instead of taking rationals or fractions, we are taking points. So it's a bit of a new notion, but yeah. So essentially, you can see that S star of n now would also be small o of n squared. Right? Okay. And similarly, we have defined it for V lambda. Since I don't have much time, so I don't want to go much into our now results. So as I promised, so these are some results we proved. And as I promised, I would like to discuss the proof of nq being 3q square over pi square plus o of q log q, and that would conclude. So everything is fine till now?
Could you repeat what are you trying to prove now? And
Yeah, so now we are basically proving that cardinality of qth Farey set is given by 3, or the asymptotic formula is given by 3q square over pi square plus O of q log q, which will prove. So, fine, anything you want to say or have doubts regarding this?
C lambda, like,
Right.
what was the motivation of taking -1 from this?
Right. So, I would like to answer that after the talk because it has some very deep reasoning, which I don't think so I have that much time to explain. But in short, the reason was to fix some points. We define some fixation and all, whatever that means. We will discuss it later. Sure. Okay. So I just erase this and prove the earlier NQ thing. Sure, everything is fine? Okay. So the major result which I wanted to prove today, which is also interestingly a Sylvester's result. Because if you check originally Sylvester's paper, he started with all of these notions and binding them together. So whatever proof we will do is originally by Sylvester. So so again we have, just to say some more words on this thing, we also have defined something known as gap between two CT visible points and two C lambda visible points, which you can check whenever the paper comes. But yeah, we have also defined, so we have done more as in, so people study about correlation of two visible points in probabilistic number theory about this visibility problem. We have done a, you can say, a step further. Instead of studying just correlation, we have also explicitly said when two points can be, said adjacent, and that adjacent has to do something with the Farey set in terms of visibility. So, as in, suppose you have located the first primitive point or the visible point on the circle C lambda, then what will be the next point? We have explicitly gave an algorithm to actually calculate that point, and that, if somebody can think, solves a bit larger amount of problems regarding different equations, because now you explicitly know how to solve Pell's equation, a particular solution given coefficients are in some particular range, and yeah, not just Pell's equation but any Diophantine equation who is a binary quadratic form. But yeah, those are some conjectures. But anyways, I don't have much time for that, so we will straight move on to
question.
yeah.
Like, have you used the actual field sequences properties, or like did you get some other properties of this new field sequence? Or
They came up naturally. We never expected them to come here. So we never used those results, but interestingly, they are in one-to-one correspondence with the Farey sets. Okay. So the claim. So I want to now prove that. So the main thing is that NQ over, so NQ is 3q square over pi square plus O of q by q. This is the thing which I want to prove. So I will start with the claim that probability that two integers are co-prime is 6 over 5, which is proving that, so we are proving Sylvester result that density is 6 over 5. Prove. So we start with the, yeah.
can't we just say, like, if a prime divides both the numbers, so in that case it's 1 by p square.
Definitely,
So
right.
basically product of 1
minus 1 over p raised to s, right.
Yeah,
So I don't want to introduce much about zeta function here, because this was not even which Sylvester thought of. This is more elementary idea, as in it just uses ideas of Morris inversion. That's why I wanted to include it here. But yeah, whatever you are saying, it's the one-line solution of this argument. Right. So I introduce some indicator function. So I define this thing as follows. It is 1 if this is the thing always 1, 0 if otherwise. So you see that our problem amounts to estimating this particular sum. Oh, okay, I've written monstrous thing. This is nothing. This just says that we are counting all those points a comma b in the unit square a comma, like not unit square, the n cross n square, given that they are co-prime. So this indicator function explicitly counts them. So the idea is to introduce this indicator function so that I can run over all those a's and b's. So this is what we want to estimate. And right, so since we have d divides a, d divides b, you can write. So you can write some conditions that a is equals to d times k, d is equals to d times k prime, and so on and so forth. And then you can just basically show that this is just equivalent to saying. So one more thing, this particular guy is also this, which is an easy exercise to do. Maybe after this.
Piyush.
Just 5 minutes. So we basically say that this is equal to this. So this guy is now equivalent to solving or estimating. Now, for some obvious reasons, if you write conditions of divisibility. So now what we use is, we estimate this floor of n over d square. So we write, so basically we can write for any x, floor of x is x minus this thing. But so interestingly, this can be also written as x square plus 4x. Okay, so this thing can be replaced by just, so a n can now be just written as n square times summation d from n d over d square plus 4 of n times summation d n 1 over d. I have just replaced this thing with this, and I am doing so now. I think so. I am using this fact that this is O of log n. This is a very celebrated fact. Again, you can check a proof of this if you don't know. So this thing comes out to be n square times summation d from 1 to n d over d square plus O of n log. So you see, we have got the error part. So this big O is called the error part. Now what we want to show that this is 6 over pi square. And so by 6 over pi square, what comes into the mind? It is reciprocal of sum of reciprocals of square. So we are just going to write it in that way. So I want to just basically, so I want to take the limit now because I want to find an over n square. So anyways this n square will get cancelled out. So what I want to compute is this funny guy. This funny guy. And this thing is just, so we use the fact that, the earlier fact that this thing is 1 if m is 1, 0 if m is greater than 1. Using this fact, you can consider this thing. I know I am rushing, but Arjun will kill me if I not do that. So this is, so you prove that this is 1, and this guy is pi square over 6. So that's why it has some really nice connection with 1 over zeta 2, or basically pi square over 6. So essentially you have got that this thing is 6 over pi square. So that proves that, so that proves the first claim that probability that two integers are co-prime is 6 over pi square. Now I just give, just now 2 minutes, I just give a rough sketch of why that NQ is 3q square over pi square, which you can just see that it is somewhat a half of that, but really there is nothing role play of half, but it is about the summatory function which I defined earlier. So what we want to estimate is this funny guy. So check that one can write this. So one can write not this thing. One can write phi n as, or one can observe phi n as in this, which is again Mobius inversion in a way. But I don't think so you require to say anything explicitly about Mobius inversion. You can check it through just writing n as it's in its prime factorization and can observe that this is true. So when you plug it here, this comprise, so essentially I want to bound this thing, right? If I know this thing, then I'm done. So this is just equivalent to bounding this thing. And interestingly, this is this. MD. You use the fact that summation m is x, so summation m where m is less than x is x square plus o of x, and then this thing will also come out to be this. So this whole thing will come out to be this thing. And now you know, so n square will come off mu d over d square, again the same calculation, this will show, but now there is the half. So this essentially will give you 3q square over pi square when you take limit n tends to infinity. Oh, and of course it's big O, so anyways that half thing will really not matter. So q log, and that completes the proof. I know I'm rushed, but yeah, that also concludes the talk. Thank you. Any questions you can ask me? As in, so which one? The S star. Yeah. So, of course, we don't want to define it using invisibility. We wanted to define it using visibility. I think when the points are visible. So we define. So instead of saying there exists, there existing is the condition for when the point is invisible. So the strong condition was that if there does not exist any such C comma D, then you say it's visible. So we just replace that there exists with there does not exist, and we said that that set is itself, you know, circular Farey set. So you know, like this in a way is a good way because we have used the both ways. We have used the fact that how to manipulate there existing and also how to manipulate that there does not exist. Because with the there existing we have proved the asymptotic thing, and from there does not exist we have found the reference like the Farey set. Right? Anything else? So you can of course catch me after this also. I am the one here anyways. So okay. Thanks.